A series, the sum of an, is called absolutely convergent if the sum of the absolute value of an is also convergent. The idea of this is that if I have some series an is equal to a1 plus a2 plus a3, if I take the absolute value of that series and it is convergent, then some other series where it might be a1 minus a2 plus a3 minus a4, where there are some terms that are not necessarily positive. If the series that is positive is convergent, then some other series where it's the same set of numbers, but some of them are being subtracted, then since the sum of that series is getting smaller faster, then it must also be convergent. That's basically the logic behind it. So let's look at what people might use this for. So we'll look at a couple of series that we already know if they're convergent or not, and then we'll look at one where it's not so obvious. So to have an idea of how to apply this logic, take this series, minus 1 raised to the n minus 1 over n squared, which is equal to 1 minus 2 squared plus 1 over 3 squared minus 1 over 4 squared, etc. If you take the absolute value of this, it is equal to 1 over n squared, which is known to be convergent. Since it is convergent, then it is said to be absolutely convergent. And if this is absolutely convergent, then some other combination where we're subtracting things and adding things must also be convergent as well. That's basically the logic behind the idea of finding out if something is absolutely convergent or not, is to go back and say, well, if this is absolutely convergent, then I know this is absolutely convergent. Then I can go back and say, well, then this must also be convergent as well. But it won't always be that way. Take the example of minus 1 raised to n minus 1 over n. 1 minus 1 half plus 1 third minus 1 fourth. This is an alternating series, but this alternating series is known, we already know it's convergent. But if we take the absolute value, it will be equal to 1 over n, which we know not to be convergent. So this is said to be conditionally convergent. So I cannot use that reverse logic and say, well, since this is convergent, because it's not, then this also must be convergent. But it does not necessarily mean, since this is not convergent, that this won't be convergent, because this is bigger than this is. This may be able to approach 0 fast enough, and it does. So this is convergent. But the point of learning this is when we get a situation like the sum of cosine n over n squared, it's not so obvious if it's convergent or not. So the idea is, okay, we've got cosine 1 over 1 plus cosine 2 over 2 squared plus cosine 3 over 3 squared. Take the absolute value of this. This is the absolute value of cosine n over n squared. That's, the bottom part's easy enough. Now the absolute value of cosine n. I know the values of cosine n to be between minus 1 and 1. So taking the absolute value of cosine n, I can say that it is less than or equal to 1 over n squared. The cosine n can be any number between minus 1 and 1. And if 1 over n squared is convergent, then a number smaller, 1 half, 1 third, 1 fourth, is also going to be convergent as well. So since this is absolutely convergent, I've just approximated it to 1 over n squared. This is the largest value it can possibly be. Therefore, the smaller values, and this is convergent, then something smaller than this will also be convergent as well. So I can say, since this is absolutely convergent, this must also be convergent as well.